specifically creating effective instructional media, often, in places where resources might be tight.
And that practical angle, that necessity, really shapes this whole discussion, doesn't it?
Yeah.
It's not all high-tech flash.
Not at all.
We're looking at a curriculum that values systematic design, sure, and ICT skills, but it puts just as much weight on, well, ingenious improvisation, making your own teaching materials. It's kind of like a teacher's survival guide.
It really is. And we're going to focus quite a bit on Module 3, which is all about instructional media production. That's the real engine room here.
Right.
It covers everything from basic tracing and copying techniques all the way to improvisation methods and even lettering. It's the practical heart of it.
Okay, so let's start right at the beginning. Educational technology. If you ask most people, on the street, what that means.
They'll say computers, projectors, smart boards.
Exactly. Hardware. But this curriculum guide, it flags that immediately, doesn't it? It says that's a wrong interpretation.
Yeah.
Or at least incomplete.
A fundamental misconception, yeah. The course really aims to broaden that understanding way beyond just the machines themselves.
Okay, so if it's not just the gadgets, how did the specialists, the people who designed this course, how did they define ET?
Well, they kind of look at it in two ways that have to work together. There's the simple sort of literary definition first, which is just, applying a body of knowledge technology to solve educational problems. Pretty straightforward. Using what we know to teach better.
Makes sense. Using tools and methods.
But then there's the specialist view, and this is where it gets more structured, splitting ET into two critical parts, ETI and ET2.
Right, ETI and ET2. Let's break those down. ETI is the hardware one.
That's the one everyone thinks of first. Technology and Education, or ETI. It's the hardware approach, applying machines, gadgets, equipment.
With the physical skills like audio players, slides, videos, computers.
Exactly. Anything tangible you bring into the classroom to deliver information, they're the means, you could say.
Okay, the tools, got it. So what about ET2? Technology of Education. That sounds more theoretical.
It is. It's the systematic core. ET2 is all about applying theories, laws, established procedures to make sure education is high quality. It's the planning, the structure, the why behind the lesson, the evaluation. It's the whole organized process.
So drawing on things like communication theory, psychology, even philosophy maybe, to design the lesson before you even pick the tool.
Absolutely. Think about the systems approach that's key to ET2. It basically says teaching should follow a logical path. You figure out what students need to learn, that's your input.
Okay.
Then you design and deliver the lesson, the process. You measure if they learned it, the output. And then, importantly, you use those results to tweak and improve everything for next time feedback or evaluation.
That's a really clear cycle. So if a teacher sees students struggling with, say, 3D shapes, that's the input.
Right.
Then ET2, the systems approach, guides them to figure out the best process, which might mean deciding that a physical model, ETI media, is the best way to teach it.
Precisely. And it links straight to psychology, too.
Yeah.
The curriculum mentions B.F. Skinner, for example.
Oh, yeah, behaviorism.
His ideas about immediate feedback, like in his old teaching machines or programmed learning, that's the foundation for how feedback works in modern computer-based learning, CAL or e-learning. ET2 provides that theoretical map.
So ETI is the tools. ETT is the how and why the system and when you put them together.
You get the big picture. Educational technology third, or ET3. It's not really a third type. It's the synthesis.
It's a combination.
Yeah, the blend of the machines and media from ETI with the systematic design and theory from ET2, they work together as one integrated system to achieve the learning goals. So when this course asks teachers to actually produce their own media, it's forcing them to do ET3, to take the plan, the theory, ET2, and make it real using physical stuff, maybe even stuff they improvised, ETI.
That makes so much sense. That jump from planning to actually making something tangible. That's why Module 3, the production module, is so central. It gives you the skills to actually build that bridge in a real classroom.
Okay, let's dive into that module then. Unit 1. Techniques of Instructional Media Production. This really gets us away from the abstract systems idea and into the nitty-gritty of actually creating things. It starts with 3 levels of production, right, based on originality.
That's right. And these levels are important because they set expectations for the teacher as a producer. They also highlight something crucial about making things locally, which is that the materials you make yourself are almost guaranteed to be relevant, appropriate for your students, and kind of validated by your specific context. Yeah. Unlike, generic stuff you might buy or import.
Good point. Okay, so the first level.
The simplest one is imitative media production. This is basically just following a pattern or instructions someone else set.
Like copying.
Yeah, like copying a picture from a textbook onto a bigger chart or tracing a diagram the ministry sent out. You're just trying to accurately reproduce something that already exists, meet a standard. It's about execution.
So if I download a worksheet template online and just fill it in exactly as shown, that's imitative, following the recipe.
Exactly. But now, let's say you look at that worksheet or maybe a diagram from overseas and you realize the examples may be pictures of, I don't know, snow-covered trees don't make any sense for your students.
Right, not relevant.
You need to change it. That brings us to the second level, adaptive media production.
Okay, now we're getting creative. A little bit, anyway. A little bit, yeah. Adaptive production still uses an original model or prototype as a guide, but the teacher makes an innovative, positive change.
So like swapping out those snowy trees for local palm trees.
Exactly. Or maybe adjusting the scale of a diagram to fit perfectly on the only available chalkboard space. It means using your own judgment, your own ingenuity, to make the original better suited to your specific situation. It requires some self-direction.
So taking that downloaded worksheet, maybe redesigning the layout slightly, translating a key term into the local language, and replacing all the foreign examples with things the students actually know. It's definitely adaptive.
Absolutely. And then you have the top level, the peak, really, creative media production.
Okay, this sounds like starting from scratch.
It is. This is where the teacher defines a problem and comes up with a completely original solution. No templates, no existing directions to follow. It's pure original thinking in the design, the materials you choose, how you put it together.
So the teacher is basically inventing the teaching tool based on their understanding of the learning need, ET2, and their own making skills. Total resourcefulness.
That's the ideal. But what's interesting is that even for the simplest level, imitative, this curriculum insists you need basic analog skills first, like really fundamental stuff.
Before you even think about fancy software.
Right. You need precision in things like tracing and copying.
Okay, let's get into those analog skills. First up is tracing, which the guide defines as reproducing the exact same size using some kind of transfer medium. And it gives 3 ways to do it.
Yeah, 3 main methods, each with pros and cons. The most basic is probably carbon paper.
The old blue or black stuff.
Exactly. It's cheap, it works, but it's really best for smaller drawings. If you're tracing something large, it's easy for the papers to shift slightly.
And then your lines are off.
Right. Registration gets messed up. The key is you put the original on top, carbon paper in the middle, making sure the carbon side is down, and your clean paper underneath, and pin everything down securely.
Okay, method 2.
Tracing paper. This is that thin see-through paper.
Like architects use.
Draftsman, yeah. You put it over the original, and because it's translucent, enough light comes through that you can see the lines underneath and trace them directly onto the tracing paper.
So you can do larger images than with carbon paper.
Generally, yes. The downside is your final drawing is on the tracing paper, which can be a bit flimsy.
Right. Might not be sturdy enough for a classroom chart.
Maybe not. Which leads to the third method, the most technically involved for tracing the light box.
This needs electricity, right?
It does. It's basically a box with lights inside fluorescent tubes, usually, and a translucent top surface, often white perspex. You put your original drawing on the perspex.
And the light shines up through it.
Exactly.
Right.
It makes the original image really bright, so you can easily see it even through fairly thick paper that you place on top to copy onto.
Kind of like using an old overhead projector as a tracing table?
Very similar principle, yeah. It gives you a really clear image and lets you use sturdy, final paper.
Okay, so that's tracing for same-size copies. But often in a classroom, you need things bigger. Posters, charts. That brings us to copying, which includes enlargement or reduction.
And this is where some really clever low-tech methods come in. The first one is fundamental, the grid method, sometimes called squaring up.
Ah, I think I've seen this. You draw squares all over the original.
Exactly. It's like analog pixelation almost. You draw a grid of identical squares over the small picture you want to enlarge. Let's say you number them, like 1A, 1B, 2A, 2B, and so on.
Okay.
Then you draw a corresponding grid on your big piece of paper where the final chart will be. Now, here's the key. If you want to make the drawing, say, 3 times bigger.
Your new squares need to be 3 times bigger.
Precisely. If the original squares were 1 centimeter by 1 centimeter, your new squares are 3 centimeters by 3 centimeters. If you wanted to reduce it, say make it 1/4 the size, you'd divide. Your new squares would be 0.25 centimeters by 0.25 centimeters.
And then you just copy what's inside square 1A of the original into square 1A of the new bigger grid, and so on for all the squares.
You got it. You meticulously copy the lines, the curves, the shapes from each small square into the corresponding bigger or smaller square. It forces you to keep everything in proportion.
That's brilliant, and so necessary if you're drawing like a map or a biological diagram for the whole class to see, and you don't have a projector or a large format printer. It guarantees accuracy.
It's an indispensable skill in those situations. Now, the other method for scaling is maybe even more ingenious mechanically, the pantograph method.
Right, the pantograph. I remember seeing these. It's that folding contraption made of wood or metal strips.
Usually 4 strips, yeah, hinged together in a parallelogram shape with lots of little holes drilled along them. It's a fantastic piece of simple engineering.
So how does it work? You need a flat surface.
A smooth board, yes. And there are 3 key points you need to manage: the pivot point, the tracing pin, and the pencil. For enlargement, you typically fix the pivot point, let's call it A, to one corner of your drawing board. Then you put the tracing pin, B, into one of the holes and the pencil, C, into another hole further away from the pivot.
And those holes matter, right? They set the ratio.
Exactly. The position of the hinges and the specific holes you choose for the pin and pencil, points D and E in the source diagram, lock in a fixed geometric ratio. So, as you carefully move the tracing pin to follow the lines of your small original drawing,
The pencil C moves further.
and draws the same shape but bigger, maybe 2 times bigger or 3 times depending on the hole settings, it automatically scales it up based on the parallelogram's geometry.
That's clever. But the guide mentioned it works for reduction too.
Yeah.
This is the really elegant part. You just swap the tools.
Swap the pencil and the pin.
Exactly. You put the pencil in the inner position, B, closer to the pivot, and the tracing pin in the outer position, C. Now, you trace the outline of your large original image with the pin.
And the pencil, being closer to the pivot, draws a smaller version. Precisely. A proportionally reduced copy. By changing which holes you use for the hinges and the tools, you can select different fixed ratios, like 2.1, 3.1, 4.1. It's like a mechanical calculator for scaling drawings.
Okay, so mastering these techniques, tracing, grid, pantograph, gives teachers the power to reproduce and scale images accurately. And that leads us straight into Unit 2, improvisation. This feels like the absolute core skill for a teacher working with limited resources.
It really is arguably the most vital practical skill in the whole curriculum, especially for achieving self-reliance in the classroom.
And we need to be clear, right? Improvisation here doesn't mean just making stuff up randomly. It's more strategic.
Absolutely. The guide defines it very carefully, providing a substitute for something specific that isn't readily available, and doing it by using locally sourced materials to meet a very particular instructional need you've already identified.
So it connects right back to that ET2 planning, identifying the need first.
Exactly. It's problem solving in action, driven by the reality of economics and resource scarcity. It's about finding ways to teach effectively without relying on expensive imports.
That's a powerful message. So when does the curriculum say a teacher needs to improvise? What are the triggers?
The source gives 4 very practical classroom situations. First, obviously, when the real thing, the actual media or object, is just plain scarce or unavailable. You simply can't get it.
Like a specific scientific model, maybe?
Could be. Second, when the real thing exists, but you don't have enough for everyone. If you only have one microscope for 30 kids, that's not effective hands-on learning. An improvised model everyone can see or touch might be better.
Okay.
Cost.
When the real media is just too expensive for the school's budget or the teacher's pocket.
A very common reality.
And fourth, this is important, when the real thing is too fragile or dangerous or maybe even spoils quickly. Think about dissecting delicate organs or handling hazardous chemicals or showing parts of the human body. An improvised model can make that learning safe and repeatable. Right. In all those cases, the homemade version actually serves the teaching goal better. It makes the concept concrete, safe, and accessible for everyone.
Exactly. And this brings us to the real how-to. The guide gets very specific, especially about using paper pulp or papier-mâché.
Papier-mâché. I remember doing this as a kid, but this sounds more rigorous.
It is presented as a proper technique. It's shown as a way to turn waste paper, something readily available, into durable, 3-dimensional teaching aids.
Like what? What could a teacher make?
The guide suggests things like models of the digestive system, maybe topographical maps with raised mountains, even a large abacus for teaching math. Things with shape and form.
Okay, so walk us through the steps. It sounds almost like a recipe. How do you make this stuff properly?
It's quite systematic. There are about 8 steps listed. First, you tear up waste paper, newspaper, old worksheets, whatever, into small pieces.
Okay, easy enough.
Then, two, you have to soak those pieces thoroughly in water. Let them get really saturated. Step 3 is key. You pound the soaked paper, usually in a mortar. You really mash it up.
Why pounding? Why not just mix it?
Pounding breaks down the paper fibers, the cellulose. It makes the pulp much more uniform and smooth, which is essential for molding fine details later.
Ah, okay. That makes sense. What's next?
While the paper's soaking or being pounded, you prepare some starch. This is your binder, the glue, often made from local cassava or corn flour, probably.
Okay.
Then you mix the pounded paper pulp with the starch you prepared. And 6, getting the proportion right is critical. Too little starch, and your model will be weak and crumbly when it dries.
Too much.
Too much starch makes it overly sticky, hard to work with, and it might not dry properly or might crack. So proportional quantity is stressed.
Got it.
Step 7 is kneading. You work the mixture like dough until it's completely smooth, no lumps. This ensures the starch is evenly distributed and the pulp binds well.
And
Finally, 8. This smooth kneaded pulp is ready. You can now use it for molding whatever shape you need for your lesson.
that is detailed. It shows this isn't just arts and crafts. It's presented as a reliable method for creating instructional materials when you have almost nothing else.
Exactly. And it's important to note, the guide doesn't only talk about papier-mâché, it recognizes its limits.
Right. It's good for curves and 3D shapes, but maybe not for everything.
Precisely. The source specifically mentions other easily available materials like cardboards, hardboards, even plywood.
Why would you need those?
For things where you need rigidity, flatness, or structural strength that paper pulp can't provide easily.
Like what?
Well, think about making simple slides for an old slide projector. Papier-mâché won't work. Or if you're actually building the arms for that pantograph we talked about earlier.
Ah, right. You need straight, strong pieces.
Exactly. Or building a sturdy frame for an abacus. Cardboard or thin plywood is perfect. Using these cheap local materials directly empowers the teacher, makes them less reliant on waiting for expensive, possibly fragile imported goods.
Okay, so we've designed the lesson, ET2, chosen our production approach, imitative, adaptive, creative, scaled it using tracing or copying, maybe even built it from scratch using papier-mâché or cardboard. But now people need to be able to read it.
Exactly. A fantastic model or chart is useless if the labels are messy or illegible. That brings us to Unit 3, lettering.
Which the guide calls the art of writing or constructing letters for functional reasons.
That word constructing is important. It's not just about handwriting, it's about building clear letters. This is absolutely essential for titling charts, labeling diagrams on posters, adding captions to models. If the lettering fails, the communication fails.
Makes sense. And the guide breaks down letter types, right, into two main groups.
That's right. The fundamental split is between block letters, which are systematically constructed, and script letters, which are essentially free handwriting.
Okay, let's focus on the block letters first, since they seem most relevant for clear classroom visuals. The first style mentioned is Gothic.
Yes, Gothic. The key characteristics here are uniformity and rigidity. All the strokes that make up the letter have the same thickness.
So no thick and thin parts.
Nope, uniformly thick. And critically, Gothic letters have no serifs.
Serifs, those little feet or finishing strokes on the ends of letters, like in Times New Roman.
Exactly. Gothic doesn't have those. It's very clean, very blocky. Because of this thickness and clarity, it's the go-to style for things that need to be read easily from a distance. Think signposts, posters, billboards.
Or a chart at the back of a large classroom.
Precisely. If you need maximum legibility from afar, Gothic is your best bet. It has high impact.
Okay. What's the other type of block letter? Romans.
Romans. The guide describes these as more romantic in nature, which is a funny way of putting it.
How so?
Because they usually do have variations in thickness. The vertical strokes might be thick, while the horizontal or curved strokes are thinner. And Romans typically do have serifs.
So they look a bit more decorative
Right.
or traditional.
Yeah, more ornate, more classical, perhaps.
Yeah.
You might use Romans for a main title on a handout that people will see up close, or where you want a slightly more formal look, but you sacrifice some of that instant long-distance readability you get with Gothic.
Got it. Gothic for distance clarity, Romans for a bit more style up close. And the other main category was script letters.
Right, script letters are just defined as letters written freehand, cursive writing, basically. And the art of doing that beautifully is called calligraphy.
Which is lovely, but probably not the most practical for labeling a diagram quickly and clearly for a class.
Generally, no. For most instructional media where clarity is paramount, those constructed block letters, especially Gothic, are usually considered more functional.
Okay, so it all fits together then. The theory, ET2, informs the need, the production techniques, imitative, adaptive, creative, tracing, copying, improvisation, provide the how-to, and lettering ensures the final product actually communicates effectively. It's a whole system for teacher self-sufficiency. Hashtag tag outro.
Yeah, when you lay it all out, the amount of practical, hands-on skill this curriculum demands is pretty striking. We've pulled out the essence of Module 3, understanding the levels of production, mastering those precise analog scaling techniques, and embracing improvisation, right down to the specifics of mixing papier-mâché or choosing the right cardboard.
It really paints a picture of a teacher who's equipped to teach effectively no matter what resources are or aren't available. Which leaves us with a final thought, something for you, the listener, to consider. Later parts of this same EDU 632 course guide do cover more advanced stuff. Computer-assisted learning, e-learning, broadcast media are all in there.
They are, yeah.
But the foundation, the skills presented is absolutely essential right at the start, are these seemingly low-tech analog abilities.
Yeah.
Mastering tracing paper, understanding the mechanics of a pantograph, knowing how to literally build teaching aids by hand from waste materials.
It makes you wonder, doesn't it? Why does a curriculum designed for modern education, which includes ICT and distance learning, put such emphasis, such detailed emphasis, on mastering the GLID method or getting the starch-to-pulp ratio just right?
Yeah. What does that insistence on ingenious manual creation tell us about what's truly fundamental to being a teacher? Is that ability to adapt, to improvise, to make something from nearly nothing using systematic thought? Is that the ultimate timeless skill? Something that matters more than any specific piece of technology that might become obsolete?
It certainly suggests that while the delivery methods evolve, the core ability of a teacher to take a concept and make it tangible, understandable, remains absolutely central.
Definitely food for thought. Thanks for joining us on this deep dive into instructional media production.